Dr. Aneela. I'm working as Assistant Professor in Department of Physics, B.V. Razu Institute of Technology, Mirzapur. My course name is Applied Physics. Today I'm going to discuss on the topic of semiconductor laser. Outline of my presentation goes like this. So first I'll discuss about the semiconductor laser and types of semiconductor laser and its construction, working, applications and drawbacks. After that, I'll discuss about the applications of lasers in many fields. So major fields, I'll explain applications of lasers. So finally, I'll summarize today's class. So coming to the introduction of semiconductor laser. Basically, semiconductor laser is a fabricated with PN junction diode when it is connected to the forward biased. So majorly semiconductor diode lasers have two types. Those are homojunction diode laser and second one is heterojunction diode laser. So the homojunction diode laser means, so in case of homojunction diode laser, PN junction diode is formed with a single crystalline material. So that means so that the basic material is same on both sides. So the example for the homojunction diode laser is single crystal of gallium arsenide. So in case of heterojunction diode laser, the PN junction diode is formed with two different semiconducting materials. Means the material on one side of the junction differs from that of the other side. So it means two different materials are used in case of heterojunction laser. So the example for the heterojunction laser is gallium arsenide and gallium aluminum arsenide and indium gallium phosphide. It means layered by layered structure comes under this heterojunction diode laser. Okay. So the working and principle is same for the homojunction laser as well as heterojunction laser. There is a little difference in construction. So in case of homojunction laser, single crystalline material is used. And in case of heterojunction laser, two different semiconducting materials are used. Okay, today I'll explain about the homojunction diode laser. So the main principle for this homojunction diode laser is the recombination of electron hole pairs. So here we are using the semiconducting material, right? So that semiconducting material should satisfy some characteristics and some conditions. So the first condition is the user semiconductor should be a direct bandgap semiconductor. So generally the semiconductors are two types. So those are direct bandgap semiconductor and indirect bandgap semiconductor. So I'll tell you the first basic difference between direct bandgap semiconductor and indirect bandgap semiconductor. So here this image shows that this is the energy band diagram for the direct bandgap semiconductor and the indirect bandgap semiconductor. So in case of direct bandgap semiconductor, here there is a valence band and conduction band. So the electron hole pair recombination occurs without changing any momentum values of the vector. So here the top of the valency band and bottom of the conduction band appears at the same values of momentum vector. And the emitted energy in the form of photons in case of direct bandgap semiconductor. So there is no change in momentum vectors. So it appears at the same values at the top of the valency band and at the bottom of the conduction band. Okay, so those semiconductors are called as direct bandgap semiconductors. So in case of indirect bandgap semiconductors, so the electron hole recombination occurs at the different values of momentum vectors. It means the top of the valency band and bottom of the conduction band will not appear at the same values of K. And the emitted energy is in the form of phonons, that is nothing but in the form of heat. So those type of semiconductors are called as indirect bandgap semiconductors. So in case of semiconductor diode laser, so the used semiconductor should be a direct bandgap semiconductor. That is the first condition. So if it is a direct bandgap semiconductor, so there is a large possibility for the direct recombination of electron and hole. so that the emitted energy is more, so that the lasing action can be done more. Okay, so that is the first condition. And the second property is it should be degenerative semiconductor. So degenerative semiconductor means, so whatever we are using the PN junction diode, generally the semiconductor diode laser is fabricated with the PN junction diode. That PN junction diode should be a heavily doped semiconductor. So that the more number of electron hole pairs are available, so it will generate the more number of electron hole pairs, so that the more number of photons are emitted, so that the lasing action can be done more. So this is the user semiconductor should satisfy these two conditions. It should be a direct band gap semiconductor and it should be a degenerative semiconductor. It means the PN junction diode should be heavily doped semiconductor is used. So the main principle for this homojunction diode laser is the recombination of electron hole pairs. So, as I am discussing about the homojunction semiconductor laser, so it has some characteristics. So, here the first type of semiconductor is homojunction semiconductor laser, and here active medium is PN junction diode laser, and the active center is recombination of electron and holes at the depletion region, and here the pumping source is direct pumping. And the optical resonator is nothing but the combination of two mirrors. So here the optical resonator, the PN junction diode acts as an optical resonator. So at the junction, the P and N regions are polished with the silver material, so it will act as an optical resonator. And the power output is in semiconductor diode laser, that is 1 milliwatt. And here the nature of output coming from this semiconductor diode laser is the mostly it should be a pulsed mode, and rarely it comes out as a continuous mode. The wavelength coming from this laser source is 8400 angstroms to 8600 angstroms. And here for homojunction semiconductor laser, so we are using the gallium arsenide is the example. So for that the band gap is 1.44 electron volt. So these are the few characteristics, the homojunction characteristics of homojunction diode laser. Next, coming to the construction of homojunction diode laser. So this is a schematic diagram of the gallium arsenide diode laser. So here for any laser, three essential components are required. Those are active medium, optical resonator, and pumping source or energy source. So here the active medium is the PN junction diode. So here the PN junction diode is made from the single crystalline material. So that is gallium arsenide. It acts as an active medium. Okay, and here the P and N regions are heavily doped. So the P region is doped with the germanium and the N region is doped with the tellurium respectively. Okay. So the next component is optical resonator. So optical resonator is basically a combination of two mirrors. So here at the junction, the P and N regions are coated with the silver material. So one side it is a fully coated polished phase, and the other side it is partially polished phase. So it means it allows the emitted light in one direction. So the emitted light can travel in this direction. Okay. So and the next one is energy source or pumping source. So for that here at the top and bottom surface two electrodes are fixed. So it allows to flow of current to the diode when it is connected to the biased mode. So coming to the working of semiconductor diode laser. So this working I will explain with the energy band diagram of a PN junction diode. So here figure A represents the energy band diagram for the PN junction diode when it is in equilibrium state. The figure P represents the heavily doped PN junction diode when it is connected in the forward biased condition. Okay. So here, if you observe the figure A, so here the position of Fermi energy level, is in P side it is enters into the valency band, in N side it is enters into the conduction band. Okay. So that from that we can say that the Fermi level, based on the Fermi level position, so we can say that the PN junction diode is heavily doped. So generally, at this point we have already discussed in semiconductor physics. So semiconductors are basically classified into two types. So one is intrinsic semiconductor and one is extrinsic semiconductor. So in case of intrinsic semiconductor, so the Fermi level position is midway between the conduction band and the valency band. So if you see this, for example, so this is the conduction band and this is the valency band. So in case of intrinsic semiconductor, the Fermi level position is here, EF. So in case of intrinsic semiconductor, the Fermi level position is midway between the conduction band and valency band. Means we have also proved that EF is equals to EC plus EV by 2. Okay, so from this we can say that Fermi level position is, in case of intrinsic semiconductor, it is midway between the conduction band and the valency band. But in case of extrinsic semiconductors, again extrinsic semiconductors of two types, P-type semiconductor and the N-type semiconductor. So in P-type semiconductor, the Fermi level position is very close to the conduction band, and in case of N-type semiconductor, the Fermi level position is close to the conduction band. Okay. So whenever we increase the concentration of doping concentration, so in P side, the Fermi level position is enters into the valency band. In case of N-type semiconductor, so the Fermi level position is enters into the conduction band. So if you observe this figure, the Fermi level position in P side it enters into the valency band, in N side it is enters into the conduction band. So that from that we can say that the PN junction diode is heavily doped diode. Okay. So here, if you observe in P side, so the conduction band contains a few number of electrons, and valency band contains the more number of electrons. So more number of electrons present in the valency band, very few electrons are present in the conduction band. In N side, very few holes are present in the valency band, more number of electrons are present in the conduction band. So whenever the electron makes a transition from conduction band to valency band, so it emits the radiation. So that radiation is equals to the EC minus EV, which is equals to photon of energy HU. So that is EC minus EV is equals to HU. So the emitted radiation, which is equals to the difference between the conduction band and valency band, which is equals to HU, that is photon of energy. Okay. So as here we are discussing about the semiconductor diode laser. So the emitted radiation is also is as to satisfy the few characteristics of laser. So we all know that the laser light has some characteristics. So the laser light can travel in one direction, and it should be a monochromatic in nature, and the laser light has high intensity than the normal light. So these are the few characteristics of lasers. So here also, whenever the electron makes a transition from conduction band to valency band, so the emitted radiation is also satisfy the laser characteristics. So we'll see one by one. The first one is laser travels in one direction. So this can be achieved by polishing the PN junction diode. So at the junction, the P and N regions are coated with the silver material, polished with the silver material, so that it allows the emitted radiation in one single direction. So in this way, the emitted light can travel in single direction. This can be achieved in this way. And the second condition is the laser light should be monochromatic in nature. So monochromaticity is nothing but it exhibits the single color, it exhibits the single wavelength. So here this can be achieved by, so here whenever the electron falling from conduction band to valency band, so it makes a transition from conduction band to valence band, it emits the radiation, it emits the photon of energy Hu. So the emitted photons will have same frequency, so that same energy. It means that it has same wavelength. So that the emitted, all the photons emitted from this transition is same frequency, same wavelength, and same energy. So that in that way, the monochromaticity condition is also achieved. Okay. So it means that, for example, the electron makes a transition from here, that in conduction band, 2 electrons are available. In valency band, more number of holes are available. For example, if one electron coming from conduction band to valency band, it makes a transition and it will emit one photon. So it has some frequency. And the second electron is also making a transition from conduction band to valence band, and it emits a photon of energy Hu. So previous photon of energy Hu and the after energy Hu, both are having the same frequency, same wavelength, and same energy. So the emitted photons will have the same frequency, same wavelength. So in that way, it exhibits the monochromaticity. Okay, so in that way, the second condition is also achieved. And coming to the third one, so the laser light has high intensity than the normal light. So in order to get the high intense laser light, so first we need to get the more number of photons. So for that, so with this figure, we cannot achieve the more number of photons. So why? Because so here very few electrons are available in the conduction band, more number of holes are present in the valency band. So the only 2 electrons can recombine with the holes in the valency band, so that only 2 photons are emitted. Here also same case in n side. So more number of electrons are present in the conduction band, only 2 holes are present in the valency band. Only 2 electrons can recombine with the holes in the valency band, so that only 2 photons can be emitted. So, more number of photons are not achieved by this diagram. So for that, so we need to connect this energy band diagram, this PN junction diode, into forward biased condition. So if you observe this figure, so whenever the PN junction diode is connected to the forward biased, so if we increase the forward biased voltage greater than the barrier voltage, so in that case, so in both sides of the energy bands get aligned. So if the bands gets aligned, so see the conduction band electrons can easily cross the junction and comes to the p side conduction band, and in valency band holes can cross easily the junction and comes to the n side valency band. So at the junction, the more number of electrons are available in the conduction band and more number of holes are available in the valency band. So that the more number of electrons can recombine with the holes in the valency band. So the more number of photons are emitted, which is equals to Hnu is equals to E2 minus E1. So if more number of photons are emitted, so more light can be achieved and more lasing action can be done. So, and this emitted wavelength mainly depends upon the band gap of a material, and it is also depends upon the concentrations of donor and acceptor atoms present in the gallium arsenide. Okay. So, calculation of wavelength of the emitted radiation. So this mainly depends upon the energy band gap of material. So here we are discussing about the homo junction diode laser. So for that we have taken the example of gallium arsenide. So for that gallium arsenide, the band gap is 1.44 electron volts. So generally the emitted photon Hnu is equals to the band gap of energy, Ez is equals to h nu. Here h nu is the frequency, so it is equals to the c by lambda. Okay, so h is the Planck's constant, c is the velocity of light, and lambda is the wavelength. So this can be written as lambda is equals to hc by Ez. So if you substitute all these values, so we get that 8628 angstroms. So the coming output from this semiconductor diode laser is this much wavelength, 8628 angstroms. Okay. So if you consider the wavelength in micrometers and energy band gap in electron volt, so the above relation reduces to the lambda in micrometers, which is equals to 1.24 divided by Eg. So the coming wavelength mainly depends upon the energy band gap of a material. So this is the working of semiconductor diode laser. Then, okay, semiconductor diode laser. So here we are discussing about the homojunction diode laser. So it has some drawbacks. So those are the threshold current density is very large, and the only pulse mode output is obtained. So maximum times the output is as pulse mode. So rarely it comes out as a continuous mode. Okay, this is the one drawback. And the laser output has large beam divergence, and laser output has poor coherence and poor stability, and the electromagnetic field confinement is very poor. So these are the few drawbacks for homojunction lasers. So in order to overcome all these drawbacks, so if you use the heterojunction lasers instead of homojunction lasers, so there are some advantages. So those are threshold current density is very low at room temperature, and the laser output is continuous, and a high output power can be achieved even with low operating current, and the very narrow beam with high coherence and monochromaticity is achieved, and the laser output is highly stable with longer life. And so that's why with all these advantages, this heterojunction laser diodes are mostly used in the optical sources in optical fiber communication systems. So these are the few advantages. Use the heterojunction lasers instead of homojunction lasers. So next, coming to the applications of lasers. So the lasers are used in many different fields. So I'll explain a few fields. So where do we use in lasers? So the lasers are mostly used in communications. So lasers are used in optical fiber communication system to transmit the audio and video signals, and to transfer data for a very long distance without attenuation and distortion. And here this image shows that lasers are mostly used in satellite communication, and the lasers are also used in underwater communication. So as laser radiation is not absorbed by the water. So in this way the lasers are used in communication. And lasers are also mostly used in industries. So the lasers are used in welding. So here the dissimilar metals can be welded using lasers, and these lasers are widely used in electronic industry in trimming the components of integrated circuits. And lasers are also used to cut the metal sheets and wood sheets, and also lasers are also used to cut the diamonds. So this image shows cutting wood using the lasers. So mostly these are used in decorative purposes. And this is the world first diamond ring. It is cutted with lasers. And the lasers are also used for the surface treatment. Mostly these are used for the automobile industries. Okay. So basically lasers are used in medicine. So lasers are used for the eye surgeries, and lasers are also used to remove tattoos and to remove the moles, and these are also used to remove the tumors which are developed in the skin tissue. And lasers are also used in stomatology. So stomatology is nothing but it is the study of mouth and its disease. So in this way the lasers are also used in medicine. And the lasers are used in military. So most of the lasers are used in defense applications. So here the lasers are mostly used in guns to target the aims, and the lasers are also used in rangefinders. And by focusing the high energetic laser beam for a few seconds, so it will destroy the aircrafts and missiles. So in this way, the lasers are used in most defensive applications. And lasers are also used in computers. So in computers, by using lasers, large amount of information and data can be stored in CD-ROM. The storage capacity can be increased by using lasers. And this image shows the laser assembly inside a CD burner. And here this image shows the laser beam printer. So lasers are also used in computer printers. And the lasers are also used in scientific and scientific research. So the lasers are mostly used to identify the chemical bonds, and it can initiate the chemical reactions, and it also identify the nature of chemical bonds, and also it can break the molecules. And the lasers are also used to estimate the size and shape of biological cells such as erythrocytes. And here this image shows the laser scanning microscope, micrograph of human RBC cells. So it can detect the RBC cells, and the lasers are used to find the size of the dust particles. And lasers are also used to counting the atoms in isotope separation. So this image shows the lasers used in isotope separation. And lasers are also used in halography, so to record the 3D images. And lasers are also used in high security systems, and they are also used to scan the fingerprint systems. Okay, so the lasers are used to develop hidden fingerprints and to clean delicate pieces of art. So in this way, the lasers are used in many different fields. So with this, I'll summarize today's class. Today, I've discussed about the semiconductor diode laser and types of semiconductor diode lasers. And there are two types: homojunction diode laser and heterojunction diode laser. Okay, the principle for the two junction diode lasers, and I also explained its construction and working, and there are some drawbacks I have discussed. And then finally, I've discussed about the different applications of lasers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.